Hello and greetings everyone. Hopefully today you did the speeding up and slowing down activities, at least numbers 1 through 4 and hopefully number 5 as well. And when you finished 1 through 4, we tried to look for a pattern here, a pattern that would help us understand about the vector nature of acceleration. What does it mean to have a positive or a negative acceleration? So hopefully, as you noticed from your examples, you cannot tell whether something is speeding up or slowing down only from the sign of the acceleration. Now, this is probably something you thought you could do. Most people thought walking in that a positive acceleration would mean you were speeding up and a negative would mean you were slowing down. But let's review the 4 examples we did. In question number 1, you were moving away from the motion detector and had a positive velocity. You also ended up with a positive acceleration and your cart was speeding up. In number 2, you were also moving away from the motion detector, but in this case you had a negative acceleration and you were slowing down. So this seems to fit the pattern that most people walked in with. Positive acceleration, speeding up, negative acceleration, slowing down. It was number 3 when I started to get some people asking questions. Because in number 3, you were moving towards the motion detector, and so in a negative direction. You had a negative acceleration, and you were speeding up. So here's a case where you had a negative acceleration, slowing down. Then in number 3, you had a negative acceleration, you were speeding up. And then to make things even worse, in number 4, you had a negative velocity, you were moving towards the motion detector. You ended up with a positive acceleration, and you were slowing down. So now here in number 1, we had a positive acceleration speeding up and a positive acceleration slowing down. So obviously you can't just look at this sign and decide whether you're speeding up or slowing down. But there is, however, a pattern that you hopefully see in 1 through 4. Look for that pattern. Do you notice that when the acceleration is in the same direction as the motion, the object is speeding up? Look, positive velocity, positive acceleration, speeding up. Negative velocity, negative acceleration, also speeding up. And do you notice the other two? When you're moving in the opposite direction of your acceleration, positive, negative, slowing down, negative, positive, slowing down, right? You're slowing down. So here's the pattern that we have to see. And really the motion maps that we're going to do should really link this in for you, I hope. But again, the pattern is when the acceleration is in the same direction as you're moving, both positives or both negatives, you're speeding up. When the acceleration is in the opposite direction of the motion, one positive and one negative, then the object is slowing down. So let's look at number 5 here as an example of really both of these things, both of these patterns. Here we have a cart which is starting down near the motion detector. The motion detector thinks of itself as 0. You're going to give the cart an initial push up the ramp, and then you're going to watch it coast up and come back down. Right, so you're going to let it go up, come back down, and catch it just before it gets to the motion detector so you don't smack into things. So this is going to have the full motion. Okay, so what does the graphs look like? There they are. And let's look at them again. You're going away from the motion detector, a positive direction, then coming back towards the motion detector. You are slowing down on the way up and speeding up on the way down. You'll notice the little dotted line here is important. The little dotted line represents the highest position. So watch that again. Oops, sorry, let's go back here. Let's watch it one more time. At the highest position, your velocity is 0. Notice your acceleration is still negative the whole time. So let's answer the questions and see what we can analyze about this motion. First of all, we're going to have to split up the motion into 2 parts, up the hill and down the hill, because different things were happening. Up the hill is before the dotted line. Right? So while it was moving up the hill, the slope here is decreasing. The slope's getting less and less steep. However, those are all positive slopes. And, of course, on a position time graph, the slope is the cart's velocity. Now, if you'll notice, we see that on the velocity time graph. Here it has a positive velocity. It's above the time axis, but it's getting slower and slower because, remember, 0 is the time axis. So here we have a decreasing positive velocity. On the way back down the hill, we have slopes which are getting steeper and steeper, so they're increasing. we have negative slopes, they're sloping down, and of course this is still the velocity. Well, notice how that shows on this velocity time graph. After the dotted line, you have negative velocities, they're below the time axis, and they're increasing. They're getting further away from the time axis. One thing you have to remember here is that these are vector graphs, and therefore bigger negative numbers are not smaller. Bigger negative numbers are faster. So this is showing a faster and faster negative velocity. Now, as we analyze the velocity versus time graph, you will notice that the slope is constant. It's one straight line. It is a negative slope the entire time, and the slope of a velocity time graph is the car's acceleration. And look at how that's represented on the acceleration time graph. Constant, negative acceleration. So a horizontal line below the time axis. So hopefully all of these things match with your understanding of what's going on here. Now let's draw the motion map. And this is going to be kind of interesting and get to some of the patterns we were talking about. First of all, there's our position reference line, which I have rotated to be parallel to the incline. The cart starts at the bottom of the hill, and then it's moving fast because it's after you've given a push, and as it goes up the hill, it is slowing down. So notice the dots are getting closer and closer and closer together. Now my next dot is going to be at the highest point. And since after the highest point we come back down the hill, I'm going to jump a level. So instead of putting it here, I'm going to put it there. I'm not going to put two dots because it doesn't stop for any length of time. It just stops instantaneously. So I've got to jump this up. Now on the way down, it's going to speed back up. So that means the dots should get further and further apart. But how much further and further apart? Well, look at the graph. The graph is what we call in physics symmetrical. Right? It's a symmetrical graph. So is this one down here, right? Where it goes, it speeds up just as fast as it slows down. That's why its acceleration is constant. So that means the dots on the way down should be at the exact same position as the dots on the way up. See the symmetry there? So it speeds up just as fast as it slows down. Next thing we're going to do is put velocity arrows on. It has a big velocity, a fast velocity to start out, and then it gets slower and slower and slower. Notice how the velocity arrows are pointing in the positive direction, but they're getting smaller, a decreasing positive velocity. Now at the highest point, the velocity is instantaneously zero. The object is changing from going up the hill to coming down the hill. And so therefore, there is no velocity arrow on the top dot. Right? Again, highest point, zero velocity. It's changing direction at that point. Now on the next dot, it is now going down the hill. So the velocity arrow should point down the hill. But before we just draw it between the two dots like we normally do, let's again think about the symmetry of the situation. Since the acceleration is constant, that means that it is speeding up just as fast as it's slowing down. That means that its speed here should be the same as its speed here, except in the opposite direction. So the arrow on this dot should be the same size as this arrow, but pointing down. See the symmetry? The arrow on this dot should be the same size as this arrow, but pointing down. The arrow on this dot should be the same size as the arrow on that dot, but pointing down. Likewise, the arrow here should be the same as this arrow. So this is the one case where you've seen me draw with some space in between, and that's because I'm trying to match the actual velocity arrows here because of the symmetry of the situation, because the acceleration is constant, because it slows down on the way up just as fast as it speeds up on the way down. Now let's put the acceleration arrows on. Notice that the acceleration is constant, therefore they'll all be the same length, and the acceleration is always negative. So negative is down the incline, so there's the negative acceleration there, negative acceleration, negative acceleration. Now, is it accelerating at this highest point? Well, a couple things to look at. Look at the graph. At the highest point, follow the dotted line, it still has a negative acceleration. And think about it this way. If it wasn't accelerating and it wasn't moving at the top, what would it do? Well, something that's not moving and not accelerating just sticks there. It doesn't move at all. So that would mean you'd push the cart up and it'd get to the top and it would just stop and sit there. And it didn't do that. It came right back down. So it's still negatively accelerating at the top dot and all the way down. Notice again the symmetry of the situation. And so look at our pattern that we found earlier. On the way up, the acceleration arrows are pointing against the motion. The motion is up the hill, the acceleration is down the hill. And what's happening? It's slowing down. I like to think of this as the acceleration arrows are taking velocity away because they're pointing opposite. They're working against the velocity. But on the way down, the acceleration stays negative, and now the velocities are negative. So now the acceleration's pointing in the same direction, and it's helping. Right? So now it's speeding up on the way down. And really, drawing these motion maps are going to helpfully lock this in as you draw a few more. So was the velocity positive or negative? Well, really, it was both. It was positive on the way up, and then it was negative on the way down. So did it change direction? Well, definitely. Right? It did that at the highest point. At the highest point, where it was still accelerating, it was changing from going up the hill to coming back down the hill. Is the acceleration positive or negative? It's negative the whole time, and it never changed direction. However, since the direction of the motion changed, on the way up, the acceleration pointed against the motion, and therefore it was slowing down. On the way down, it was pointing with the motion and sped up. So I hope this helps to lock some of that in. And as we do some MOPs and worksheets and things over the next few days, I hope that you can lock in that idea of what a positive or a negative acceleration means. Namely, that you have to compare it to the direction you're moving to see whether it means speeding up or slowing down.